Hi everyone, welcome back. So this time let's try out an example. Okay, so what we have here is this a frame or a machine? That's the first thing I want to ask you. And the problem statement gives it away. I shouldn't have hit so many buttons. Okay, well it's a frame, but why is it a frame? It's a frame because we have one multi-force member. We've got two supports, and we also got a moment being applied to it and a force. Lots of stuff going on there. And two, all it's doing is exporting external load. It's not actually going to move. This is going to be a stationary support. So what we want to do is find the horizontal and vertical components of the pin reactions at C and the magnitude of the reaction at B. Okay, so can we do this? Why didn't they mention A? Why didn't they ask for A? We'll figure that out. So I'm going to let you go off and try this on your own, but before I do, I'll give you a plan, which is usually way too much help. But I'm still going to give you these plans because I'm a nice guy. So what we're going to do is draw a free body diagram of frame BC right here. And you're going to apply your equation of equilibrium to solve. And I might be wondering why frame BC? Well, you have to go try it on your own and see. So I'll give you 3 seconds to go do this. Of course, you can pause so you can have more time if you want. But 3, 2, 1, and we're back. So you finished it. You did it. It was so easy. You're like, oh, I got this. There's no problems. Well, just in case it wasn't that easy for you, let's look it over. Let's try it out. So first off, like I said, we got to have a free body diagram of this member BC. Now, you might be wondering, why BC? Well, let's count the unknowns, shall we? 1, 2, 3. Second thing you're wondering is like, wait a second. Wait, why is this one right here 2? This one's 1. You're just cheating. I'm not cheating because this BA is a 2-force member. It doesn't have any other external loads. Nothing there. So since it's a 2-force member, we know the direction of this force. We just don't know its magnitude. And so from that, I only have 3 unknowns. 3 unknowns, 3 equations I can solve. Now you might be wondering, well, how are we going to solve? Because we got a couple things here. Well, let's look at it and see. First off, probably some moments bound point C would be a good idea. And if you're confused, but like 800 newtons isn't applied there. It's applied over here. 800 newton meters is a couple moment. You can move that literally anywhere you want. Like the place we put it is completely arbitrary. Its effect on the overall system is the exact same. Now, its internal effect is very different depending on where you have it. But its external effect, assuming it doesn't break, is not going to change. Now I choose point C because we get rid of 2 unknowns. We only have 1 unknown right here from force AB. A little bit of a frustrating point about it is that force AB, because it is both in the horizontal and vertical direction, will have 2 components to add to the moment. You see them right here. That is us just breaking up force AB into its horizontal and vertical components. We can figure out which ones those are by looking at our slope triangle. So this one is 1, this is 3. If we're just talking about slope. And that will make this one right here the square root of 10, because that's 3 squared, which is 9, plus 1 squared, which is 1. So square root of 10. So you can see that the vertical component is 1 over square root of 10, and the horizontal component is 3 over square root of 10. So then looking at this, then I have the vertical distance times the horizontal component. So that's 1 times 3 over square root of 10. Then I have the horizontal distance times the vertical component, which is going to be 3, because that's 3 meters from here to there, times 1 over square root of 10, which we see right there, plus our moments from this force and just our regular coupled moment. All it's equal to 0, we solve, and we get that force AB is 843 newtons. Okay, that's one. What's our next one going to be? Well, we use some of the forces in the X and some of the forces in the Y. You already have the components of force AB, so you just get to reuse it now with the magnitude plugged in, and we can solve. So we see that Cx is going to be 800 newtons, but it's going to actually be the opposite direction. We've got a negative number here because we drew our arrow wrong. And then CY is going to be 133 newtons up. And once again, we drew our arrow in the wrong direction. So it happens. You can draw your arrow in the wrong direction. And if you're uncertain about if you have it right or not, don't worry about it. You'll just get a negative sign as long as you do everything else correctly. Just be consistent. Don't randomly switch arrows halfway through. Get your negative sign, and don't go back and change free body diagram. Just say like, okay, well, if I have to give a direction, I was pointing it down. Since it's negative, it's actually going up. You can write that next to your answer like they do here. I would not go back and flip your free body diagram because you will probably confuse yourself if you start changing numbers. Maybe you won't, but it's something to be careful about. Okay, so with that, I think we've gotten everything done here. That's all it's going to ask for. Yep, we're going on to the next problem. So let's end it there, and I'll see you all next time for a group problem. But remember, frames, multi-force member, we're not going back to the method of joints for this, okay? You have to do it method of, almost a method of sections. You have to break it up into its own free body diagrams. Each member gets a free body diagram. However, if it's a truss, all 2 force members, method of joint, method of sections, enjoy that. Okay, well, I'll see you all next time. I hope this helps you. Have a great day. Goodbye.